So I got everything on? Yeah, I do. All right. I'll begin with a word of prayer. So, dear Father, we thank you again for this opportunity we have just to meet and study your creation. Just pray that you'd give us understanding this morning and help us again to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I owe you guys a calculation. So let's get to it. So I introduced the quaternions at the end of the last lecture, and I mentioned that you can multiply them out, and they're really interesting formulas to see there. So let's actually do that. So the quaternions were the set of objects of the form, let's say t plus xi plus yj plus zk, such that t, x, y, and z are real numbers, and I squared equals j squared equals k squared equals -1, and ij equals to minus ji equals to k, jk equals to minus kj equals to I, and ki equals to minus ik equals to j. Now, this description I just gave is by no means minimal. Like, you can define the quaternions in a much less clumsy way than that. But that's pretty much that's pretty much everything you want to know for how to multiply them. All right. So as a point set, you can think of this as basically being 4 dimensions, like R4, where you could think about like the number 1 being this one, the imaginary, what's called the versor I, would be like 0, 1, 0, 0. The j you could think of as being 0, 0, 1, 0. And the k you could think of as being 0, 0, 0, 1. So the point is, if you have 2 quaternions, they're only equal if they're matching in both the real, the imaginary, the imaginary, and the comaginary parts. Those I just made up. I don't know the official quaternionic language. I'm not part of that cult. So anyway, I suggested that we let the quaternion z, bad language, let's say alpha equal to, let us say a, let us not say that. Let us say t plus vector r, where I'm using vector r as notation for xi plus yj plus zk. All right, and we'll let beta be equal to t, not t, rather s, plus, I need another vector, how about v? Where vector v is, let's say, ai plus bj plus ck, all right? So these would be like 2 pretty much arbitrary quaternions, and let's multiply them out, right? Simple exercise. 4 things times 4 things, there's 16 possible terms. So let's do it. So we have, but I'll write it like this because it'll save us a little bit of writing. Rather than, if I group them, if I group the terms like I have here, when we multiply it out, it's a little bit easier, you see, because we can just go, well, that's TS, right? Plus t times v vector plus s times the r vector. Remember, the real number multiplication, we can bring it to the front. We have to be careful with the quaternion multiplication, though, because those don't commute. So here we've got r times v. All right? So let's see here. We could rewrite this. I mean, we could just leave it like that. Let us focus our attention on the weird part, which is the vector times the vector, all right? You're like, wait a minute. Well, if you're taking Calc 3 right now, hopefully at some point your instructor told you cannot multiply vectors by vectors, right? Or they at least said, if you do that, you can only do if you do what? Cross product, right? I mean, we also take the dot product, but what's the deal with the dot product? The dot product gives us a number, right? Whereas the cross product gives us a vector. So if you want to take the product of two vectors and get a vector again, you better be taking a cross product. Or you're doing this. Let's see here. So r times v is equal to xi, come on, xi plus yj plus zk times ai plus bj plus ck. All right. So trinomial times trinomial, there's 9 possible terms here. I'm going to group them. So I have xai squared plus ybj squared plus zk, excuse me, zc k squared. All right, that's my sort of, I guess you could say diagonal terms. That's not quite true. And then I'm going to group other stuff, like how about I and j? What do I got? Look at this. I've got xb minus ya. Why do I have the minus ya? Times ij. So what I did there is I used the fact that ij is equal to minus ji to put a minus on that term. All right, so then how about I can also have ki terms, right? So ki terms, I've got zc minus xa times ki. The reason the minus is because x times a, x times a, what's wrong with me? Many things. But in this particular instance I'm talking about, that should be c. Whoa. Just a second, guys. Remember, I'm doing this calculation at 8:15, so all bets are off. ZA, right? Duh. ZA. Let me double check the last one. XB. YA. All right, now we're good. And finally, what's the other thing? IJKI. JK? Not a joke. Let's see here. JK. So you got this guy times that guy, which gives you a YC, minus this guy then that guy, which gives you a minus ZB. All right. So there. And let's count. Whenever you have a problem like this, you should always count and make sure you haven't missed something. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times 3, 9. That's good. That's how many terms we should have. So let's work it out then. So this is minus xa. I'm going to factor out the minus there. Minus xa minus yb plus yb plus zc. Right? That's because I squared equals j squared equals k squared equals minus 1. All right. And what was ij equal to? ij was equal to k, right? So these are just like cross products. I cross j is equal to k, so ij is k. Okay, so we got plus, let's see here. Let me do this one first. Yc minus zbi plus za minus xcj plus xb minus yak. All right. Let me switch notation a little bit so you guys can see what this is directly. Instead of using xyz, let's use x1i plus x2j plus x3k. And for v, let's use v1i plus v2j plus v3k. That should make the pattern stand out a little bit more nicely. So what we're looking at here is minus x1 v1 plus, parentheses here, x2 v2 plus x3 v3. And then over here, you've got plus x2 v3 minus x3 v2 I plus x3 v1 minus x1 v3j plus x1 v2 minus x2 v1k. I hope with those indices, some of you who have Calc 3 fresh enough on your mind ought to be able to see what I'm writing. What am I writing? Cross product, and I mean this is clearly the dot product, right? So the formula here is minus r dot v. Okay, so we need to make a distinction between that being the calculus 3 dot product as opposed to just plain old multiplication. Quaternionic multiplication has two things. It has a dot product and also what you might call the cross product, right? And so, and the general product of two quaternions, it's uglier still, right? It's like TS plus TV. I guess you could. I'm not sure what's the best, most like appealing way to write these terms I'm writing over here right now. So I'm just going to write them. But this part is the interesting part. So that's minus r dot v plus r cross v. So there you go. That's the quaternionic. I guess I can. Let me put it on one line. I feel better to put it on one line. Minus r dot v plus r cross v. So there, in that sense, the quaternions have both the dot product and the cross product built in. Now, the thing I'm projecting on the screen right now, this is a paper I wrote in 2017-ish that kind of summarizes things I learned with students about something called acalculus. So it's intended as like a primer for people who want to learn these things. And I don't think it's significantly much harder than like coursework, but it's certainly not widely known. I think it should be. I think that there are applications of this stuff to engineering which are not known. I've reached out to one of your engineering professors to talk about this, but I never got a response. They're apparently busy. Go figure. Me too, because this still is not published, but like it should be published somewhere. Anyway, so I have like a 5-page history of these other algebra systems here. It's a very incomplete and slanted history, but there it is. While I've got it up. This is fun. I got this from Wikipedia. These, like, a good number of these are all different names for one, like the hyperbolic numbers. Like about a dozen of these are, I think, hyperbolic numbers, if I remember correctly. So the funny thing is these algebraic systems, they get like discovered and rediscovered and renamed over and over again. And as you study it, you'll find that like mathematicians have forgotten this problem, and it never quite gets completed. It doesn't seem to have journals which, that sort of coalesce the knowledge and keep it in one well-understood place. And it also tends to, like, my experience has been less than. I've had some trouble with publishing some of these things because basically I run into this thing. Well, this is too easy. Basically is the response. It's like, well, yes, I'm trying to make it easy. I want students to be able to understand it. I don't want to make it complicated. It's a weird thing. In mathematics, if you don't make something complicated enough, you can't publish it. It's kind of the opposite problem. In engineering, if you make it too complicated, you probably can't publish it. Right? You'd like a simple solution, not a really complicated one, I guess. But anyway, I only had this up so that I could show you, let's see here. This is all, the only reason I had this out. I just wanted to show you guys this. These are the matrices. These matrices represent quaternions. So like if you want a matrix version of the quaternion A plus BI plus CJ plus DK, that's it. All right. So what do you think the length of the quaternion should be? Nobody? If I give you the vector ABCD, what's its length? 4. Oh, no. I think it ought to depend on A, B, C, and D, right? Yeah. So what's the length of the vector ABCD? Vector dot itself square rooted, right? So square root of A squared plus B squared plus C squared plus D squared. That should be the length if we're using the Euclidean notion of length, and we are. So I'm speculating. I think the determinant of that matrix actually gives you the length. Let's just talk about your take-home test question for just a second here, because that's pretty much the only thing I have testing you on the quaternions until the final. I mean, I probably won't, but I do like the quaternions. I don't know. Okay, so what did I ask in this problem? I was like, here's a quaternionic variable with t, x, y, and z. There's my description of the quaternions, blah, blah, blah. Oh, here I define the conjugate. See that? Eta star. So the smart, lazy way to do this problem, right, would be to use the notation I just introduced on that board over there. When you multiply eta star times eta, you don't actually have to multiply all 16 things out. You could just use my formulas adapted to this particular problem and see what happens. All right. So I will tell you this. I think what you ought to see, I believe what happens with eta star eta is you get like the squared length of the quaternion. So one of the things you could do with it is define the reciprocal of a quaternion, like the multiplicative inverse. And so it would go like this, like 1 over alpha, you could define to be alpha star divided by alpha alpha star. I think that makes sense. So don't quote me on it, but I don't think I've asked you to do that, but this is something you could do. And the interesting thing here is that any non-zero quaternion has a multiplicative inverse. It's like complex numbers in that sense. A lot of the other number systems that I have in this paper here, they're such that there's lots of things that are non-zero and yet don't have a multiplicative inverse. But anyway, I can talk to you more about that if you're interested. I won't take any more class time on that. Let's see here. So let me see if I can find. Yes, so let us talk about linear algebra proper. So we have about a half hour. Wait a minute, no. How late did I start class? 5 minutes over, right? So I get 5 minutes over, right? No? No. It doesn't work that way? I got 25 minutes to teach you the rest of 321. I think I have just enough time to confuse you, so I will do my job. But the point of this little snippet here is just to try to alert you to how things go, because you might find yourself needing to do more than just calculate with column vectors, right? And so a vector space is simply an abstract set which has an addition and a scalar multiplication which behaves like Rn. Just that. Or like Cn if you've got a complex vector space, all right? So let me just show you some examples. So here's the definition. The definition is very unexciting, but it basically says you can add vectors and you can scalar multiply them. And if you look through these properties, every last stupid one of these is something that was true for column vectors. So the set of column vectors is the quintessential example of a vector space, all right? And but here's some examples of vector spaces. Set of matrices, vector space. Complex matrices, vector space. Matrices over another field other than complex or reals, vector space over another field, whatever that is. Complex matrices, vector space, either over the complexes or over the reals. I said over. When we talk about an abstract vector space, we can choose different scalar multiplication. So you could look at vector spaces over the rational numbers, over the real numbers, over the complex numbers, or over finite fields like Z mod 2. You might be interested in that if you're like a computer scientist, right? Working over Z mod 2 is significant for like computer architecture and stuff like that, I imagine. Anyway, so this is a much more exotic example. Functions from a set to the reals. These form a vector space. Also, functions from any set to a vector space form a vector space, where you can add the functions by pointwise addition. Polynomials form a vector space. And guess what? You can also take any of these examples I've told you so far, and you can make matrices of these examples. Again, a vector space. Take any two of these examples, take the Cartesian product of them. Again, a vector space. All of these sets have a natural structure which allows the addition and scalar multiplication of vectors. So it's this is one of the things that makes 321 significantly more difficult than this course, is when I talk about a vector, I'm not just talking about this. I'm talking about an abstract object in a set which satisfies the axioms for a vector space. Right? So there's a much wider class of examples out there. But anyway, once you get that in your system, and you've got our list of examples, it's a lot like what we've already done. 0 times a vector is 0. 1 times a vector is the vector. Minus 1 times a vector is the additive negation of the vector. If you've got a constant times a vector equal to 0, either the constant 0 or the vector 0. We've used all of these things in the context of column vectors at some point or another this semester. That's not a question. That's an itch. Okay. You can also talk about subspaces. Subspaces of a vector space, that's a thing. We've talked about subspaces in a very limited context in here. Our subspaces included column space, null space, and the perpendicular to a set of vectors. I think that's it, right? So like the perpendicular set to a set of vectors, that's actually a subspace. A subspace is a vector space subject to the vector addition, which is ambient to the context. So in our context, that just means our subspace is closed under addition of vectors and scalar multiplication of vectors. That's been the case for column space, for null space, for the eigenspaces also, if you want to think about it. These are all subspaces. So one of the first things you do in 321 is you learn the subspace test. The subspace test is that if the set is a subset of the vector space and it's closed under addition and scalar multiplication, it's a subspace. There is yet a simpler subspace test, which is the span theorem. The span theorem simply says that if it's a span, it's a subspace. I'll get to that eventually in these notes, but not yet. There's other weirder examples of subspaces, like here. You could look at the set of functions on the reals such that the integral from -1 to 1 is 0. That gives a subspace because the sum of two such functions is again such a function. And if you scalar multiply such a function, it's still such a function. All right, so you can talk about spans. You can talk about linear independence, but spanning and linear independence, no longer can we just rely on our wonderful CCP, right, the column correspondence property. We actually have to work out the algebra in terms of explicit battle with the coefficients for like a lot of these examples, because you can't just chuck your vectors in a matrix and do stuff because they're no longer column vectors, so you can't just concatenate them into a matrix. You actually have to work through the algebra for the spanning condition or the linear independence condition. But really, at the heart of it, the calculations are the same. There's a reason this is a prerequisite for the other course. Let's see here. And then, so the definition of linear independence in a vector space, same as the one we had. It's just now, instead of being column vectors, they're just arbitrary vectors. And this definition is still, and it's a little bit slippery too, see, because I'm not saying S has k vectors in it. I'm saying that we take a finite subset of the set S, and if linear combinations of that equal to 0 implies that the coefficients are 0, that gives a linear independence. This definition allows for S to be infinite. That's another significant difference between this course and 321. We will think about things like infinite spanning sets in that course. All right, let me stop trying to scare you about that. I'm not trying to scare you about 321. I'm just trying to alert you to some of the differences, and I think it's worthwhile if you're thinking about a math minor and it's something that you're interested in. Don't be scared of it. You can do it if you work. Okay, so let me go on here. I don't want to teach you the whole course. We can also talk about basis, a tale of two maths. So this is one of the more significant sort of theoretical accomplishments of the course, and it's kind of, I don't know. Basically, one of the big deals in 321 is you prove that any two vector spaces, if you have two vector spaces, all right. Well, if you have a given vector space, and you have two finite sets, both of which are linearly independent, both of which span the space, all right? In other words, if you have two bases for a set, it must be the case that the number of vectors in those two bases are equal. Now, this is not entirely trivial to prove, but that's one of the things we'll prove in 321. What that means is that the definition of dimension is well defined. Anyway, let me skip ahead here a bit. You also talk about linear transformations, which now the inputs and the outputs are abstract vectors. Some of these things are familiar. I've stolen much from 321 for 221. Isomorphism is an interesting thing. Let's see here. Coordinate change. It should be easy for you guys if you stay in my course. It will be less easy if you haven't had my course. There's also something called quotient space. We don't care about that at the moment. All right, I will eventually get to where I'm going. Jordan form. Well, we talked about that. Yay. Brrr. I should have remembered the page number. All right, so all of this sets the stage for what I really wanted to talk to you about today. The interesting part, at the very end of 321 usually, Euclidean geometry. So if we take a vector space, all it has is a notion of addition and scalar multiplication. But past that, you can talk about what's called an inner product space. All right, an inner product space is a space which has basically an abstract dot product. So if you have a vector space paired with what's called inner product, this gives you an inner product space. What's an inner product? Well, it satisfies these defining conditions. Like it's linear in the first spot. You can pull constant out of the first one. It's complex conjugate, turns it around, and it's positive if x is not equal to 0. Now this is the definition for an inner product over the complexes, basically, possibly. If you specialize this to real numbers, it just becomes like the inner product of x and y is equal to the inner product of y and x. That's called symmetry. Just like dot product. Dot product of x and y is equal to the dot product of y and x, right? So the inner product is an abstraction of the essential properties of the dot product. All right, that's the idea here. And basically, you can define inner product on some of the vector spaces that I just talked about, like sets of matrices. This one is especially cool. So if I have two n by n matrices, I can define their inner product simply by multiplying corresponding components and adding them all together. Like A11, B11 plus, oh man, dot, 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 ANN, BNN. You can also do this for like for rectangular matrices. It's pretty obvious. So basically what you're doing is you're just taking the matrix and like listing it out as like a super long vector and just taking the dot product of those super long vectors to form the dot product of two matrices. All right. And I really should say inner product. In fact, there's this super sneaky, like awesome formula, the inner product of A and B, you can actually write as the trace of AB transpose. This simple matrix formula gives you all of those terms. Now I won't, admittedly, making contact with the complex examples here does require some time. And we don't have that time today. So, oh no! The double scrolling got me. Dudes. All right, some of this we have done this semester. Some of it's totally new. All right, so come on, where was I? Here was I. All right, so here is something weird and new. You can have the set of, so C upper 0, 0, 1, that's notation for continuous functions on the closed interval from 0 to 1, right? So continuous functions you can integrate, and their integral is bounded, it's finite, so that makes sense to integrate from 0 to 1. And so this integration is the analog of the dot product for the set of continuous functions. Now, we have now left the realm of finite dimensional vector spaces because there are infinitely many linearly independent functions on the set 0 to 1 that are continuous, all right? So this is a dot product, quote unquote, scare quotes here, on an infinite dimensional vector space. You can use integration to set this up. And it's easy enough to check, though, that that has the required properties like the linearity, the symmetry, and the positivity that you want. Like the integral of a square of a function, you're integrating something that's non-negative, right? So that's clearly non-negative. Because if you have one point for a continuous function which is non-zero, since continuous functions are continuous, they have to be non-zero for some whole neighborhood of the point. And if you've got non-zero for a whole neighborhood of the point, when you integrate the square of that, it has to be positive, yeah? So sometimes we even use calculus. There you go. All right, so great. Basically, the set of polynomials, you guys know what polynomials are, like 1, x, x squared, x cubed, linear combinations of those, right? Finite linear combinations of those. Those are polynomials. And polynomials can be given the structure of an inner product space simply by defining the inner product of f of x and g of x by the integral from 0 to 1 of f of x, g of x. So that gives us a dot product for polynomials, which means we can do things like decide when or not two polynomials are perpendicular. What? Yeah, two polynomials could be perpendicular. Let me show you an example of this. We also define the norm in the same way that we just did a minute ago for ABCD. You guys told me this, the length of ABCD was the square root of a dot ABCD dot ABCD, right? That generalizes the length of x in an abstract vector space. If it's an inner product space, is just the square root of the inner product of x and x. So we can define a norm, a vector length. Uh-oh. What am I saying? I rejoice in this cough. Graduation draws nigh. You can prove, well, anyway, this is stuff for another day. Trying to get to an example here, guys. Okay, so, yeah, here we go. So, W, so this time integral from minus, so the integral from, I'm talking about integral from 0 to 1 forming a dot product for functions. You see, you could just as well integrate from minus pi to pi. Or whatever, like pick any domain you want to integrate over, and you could think about the inner product defined from that. But here from minus pi to pi, and I've included a normalization of 1 over pi. With respect to that normalization, if we take the inner product of sine x with itself, sine nx with nx, we get the integral of sine squared. I know you guys love calculus too, so there it is. And oh, look at that. What's that mean about sine nx? What kind of vector is it? It is a unit vector. That's right. So sine of nx is a unit vector with respect to this notion of inner product. And you can also check that cosine of nx is a unit vector with respect to this inner product. And the constant function 1 over the square root of pi is a unit vector with respect to this function. And you can check that the inner product of sine with cosine gives you 0. That's just a Calc 2 integral. What this means is that the sine nx and cosine nx and that constant are a what? They are an orthonormal set with respect to this notion of inner product. Which means that you can rip other functions apart. You can build other functions from these functions by taking dot products with cosine and sine and the constant. And you can build another function as linear combinations of sines, cosines. and a constant in this way. This is the idea of Fourier. In about 1805, he made this crazy claim that you can build any function from a linear combination, basically, of sines and cosines, which is just crazy, right? Like, you mean to tell me I can take e to the x and build it as a sum of sines and cosines? X to the fifth plus x cubed plus x plus 3. You can build that as a sum of sines and cosines? That sounds crazy, doesn't it? Sounds a little bit crazy. So, let me get to it though. The Gram-Schmidt algorithm generalizes here. You just have to trade your dot products for inner products. I think I have an example. Let me find it. I know I have an example. I was looking last night. I'll find it again. Sorry for the scrolling. So here's Gram-Schmidt with polynomials. So let's see. I've got 1x and x squared, and 1 is perpendicular to x with respect to this inner product, but 1 and x squared are not perpendicular. X squared and x are perpendicular. So it's kind of a mixed bag. But so x already has length 1 because the integral from -1 to 1 of x dx is 1. But I think, where's my u1? Yeah, u1's that. Okay. Oh, excuse me. The integral from, wait, what? Dudes. No. Hey, what? Oh, I didn't say that. I'm just saying something I didn't say. So let me unsay what I said. Let me unsay what I didn't say here. I'll shut up. So I'm just defining u1 of x as 1. That's all I'm doing at the moment. All right. And then what am I doing here? I'm subtracting off the piece of x which is parallel to 1, which is nothing because x is already perpendicular to 1. As we see right here. And then the next step in Gram-Schmidt here, x squared, subtract off the part parallel in x to x squared, part parallel into 1 in x squared, and we get x squared minus 1/3. Now, the vectors, quote unquote, 1, x, and x squared minus 1/3, they don't have to be unit length, do they? So, I calculate the inner product of u1 with u1, u2 with u2, and u3 with u3, and we end up with needing normalization factors 1 over square root of 2, square root of 3 over 2, and finally square root of 8 over 45. But there you go. This is an orthonormal set for like quadratic polynomials. They're called they were known as Legendre polynomials. Now, all this stuff we did with orthogonal complements and projections still makes sense in the abstract inner product sense. So you still talk about perp, and so that leads us to the closest approximation, closest vector problem. We talked about that already. Let me skip ahead here. I want to show you the cool part. All right, come on. We'll get to it. So past the least squares, which is one application of all this stuff, is approximation by Fourier analysis. So if I have e to the x, is e to the x a quadratic polynomial? It is not. But I can take dot products with those Legendre polynomials I just derived and find the components of e to the x with respect to that basis. In so doing, I can find the projection of the exponential function onto the thing that's spanned by 1x and x squared. Now this is a different, like you learn an approximation for the exponential in in calculus 2 called the Maclaurin series, right? 1 plus x plus 1/2 x squared is the natural Maclaurin series approximation for the quadratic piece. This is a little bit different though. If we take the projection of the exponential with respect to the Legendre basis, we get 1.03 plus this plus that. That is a different approximation to the exponential. Now, going back to the cosines and sines, it turns out like what motivated Fourier to look at expansions of functions into sines and cosines was he studied at least three. I'm not sure what he studied exactly, but I know he studied the heat equation. And the heat equation, excuse me, the heat equation studies the flow of heat through a solid through what's called diffusion. And the kind of differential equation you get, it ends up that if you assume that your solution is a sum of sines or cosines, you can actually work out the form of the solution through something called separation of variables. And so I think it was partly that which led Fourier to make this crazy claim about any function being built from a sum of sines and cosines, which was completely just nonsense at the time in terms of like what was known mathematically, in terms of the analysis, like rigorously done. Rigorous analysis wasn't a thing at this point. It was this question by Fourier which actually led to the invention of what we now call real analysis. So the evil that you face as a math major in your senior year, it's all Fourier's fault, really. But anyway, so here we go. These are so this right here, with respect to the minus pi to pi, is an orthonormal basis for the set of sines and cosines. And so I can take dot products with respect to those guys of an arbitrary function, and I can decompose the function into a sum of sines and cosines in so doing. Like here, a square wave goes from -1 to 1, all right? And I can project that onto the sets of sines and cosines by just taking inner products with sine and cosine of the function, which amounts to doing these integrals. Many of them are 0. Some of them are not. Infinitely many of them are not, actually. All the sine integrals are not. And that gives us this right here. So the square wave, I don't know if you can see it or not. It's just, I don't think I have a graph, but square wave is just this. And so this, what you see, is higher and higher order Fourier polynomials. A Fourier polynomial is a sum of sines and cosines. And as you can see, if you take more and more, you get closer and closer to the square wave. So this, a lot of mathematicians reject it out of hand because it's got some really, really nasty features. Every sine and cosine is continuous, right? Is the square wave continuous? No. So you're telling me you can take an infinite series of continuous functions and create a discontinuous function? Yes. Yes, I am. Here it is. And so that's the kind of thing that mathematicians had to grapple with. And it took us the better part of a half century to really work that out. A lot of it ultimately sort of being settled by Riemann. You know the Riemann integral, right? That guy. Wait, no. Wrong mathematician. Weierstrass is the one more so. He's the godfather of the epsilon delta proof. You guys remember that? Yeah. Unfortunately. You're like, that's how I got a B in calculus 1. Dang it. Soprano. No. Well, I think that might be all the yeah, that's it. So Monday, we'll talk about the final exam and the solution to the take-home test. You guys got questions about take-home test? Feel free to ask me. Some of you are like, I do Graham-Schmidt on the first one and it didn't make sense. That's right, because I gave you a set which was linearly dependent, as on purpose. You need to fix that. How do you take a set and make it linearly independent? What can you do? Put the vectors into a matrix, row reduce it, pick out the columns. You can use the column correspondence property to pick out a linearly independent subset. It's not much. I think like the